So let's get started again. So just before the break, we discussed that the average test error in the conventional sense can be obtained by taking E out of GD and taking the expectation with respect to D. So the way we defined E out before is we were fixing a training set, looking at the hypothesis and taking the expectation with respect to the. So that we can write now delta of x is the bias plus the variance. So we can write it as expected value of x of the bias of x plus the variance of x. So we'll define this expected value of x of bias of x as to be the average bias and expected value of x of the variance of x to be the average variance. So what we get as an identity is that average test error, where the average is both with respect to the query point x and the training set D, is equal to the average bias plus the average variance. So this is a key property because we are interested in, given a hypothesis class, what is the average test error. And what we can show is that that is equal to the amount of average bias we have, so how good an approximation it makes for the ground truth, plus the average variance, how much fluctuations it has with respect to the training set. And we discussed before that for a hypothesis class to have a small test error, both the bias should be small and the variance should be small. So you see the trade-off between bias and variance right here. So imagine that we are plotting the bias and the variance as a function of the number of samples. So we have on the x-axis n, which is the number of samples in D. What we do is we now use this training set D, we pass it through a learning algorithm, get the output hypothesis, and we compute the bias and the variance, right? So I want to sketch, so this is the error. I want to sketch my bias function and I will do the average bias. So this is expected value of x of bias of x and the average variance. This is expected value of x of the variance of x. I want to sketch the bias and variance as a function of the number of samples on the x-axis. So can anyone tell me how the bias function will look like on this plot? Will it be increasing? Will it be decreasing? Will it be constant? So remember, bias of x is g bar of x minus f of x square. And variance of x is expected value over d of gd of x minus f of x square. This is what we had before. So if I were to take the bias for each x and then take the average with respect to x and sketch it, how will it change with the number of samples in my training set? Any ideas? Anyone thinks it's constant? No one? You think it's constant?
No.
Okay, what's your...
You said it's related to underfitting, so if you increase the number of data points, like if you fix the hypothesis, you'll be underfitting the data.
Right, so the way to think of bias is that, the best way to think of bias is that you know the ground truth f of x, right? And you're choosing the best hypothesis in H that provides you the best approximation. So you had f of x. So you had f of x that looks like this, right? And you are allowed to only draw constant lines. So you're only allowed to draw lines like this. And this was the best approximation we had. Now, what I said is this will be underfitting if h is very simple. Imagine that you have a 10th order polynomial, right? Then you can draw a much more complex polynomial. So you might get something that looks maybe like this might be your approximation if you are allowed higher order polynomials. So in that sense, I said yes, bias determines whether if the hypothesis is too simple, your bias will be large, so you'll be underfitting, and if your hypothesis is complex, your bias will be small. Yeah?
Since we're already we assume that hypothesis is the best approximation of the ground truth, the sample point shouldn't affect.
The sample point should not affect, right? So because here, the way the bias is defined is we know f of x and we are given the hypothesis class and we choose the best approximator. The definition of bias does not depend on n or even d for that matter, right? It's just a function of the hypothesis class and the ground truth. So you're right that the bias is actually a constant function. So this is how bias of x will be. Now if your hypothesis class is complex, then the bias will be lower. It will be somewhere here, right? So this is for maybe simple h, and if this will be for complex h. Okay? So the bias does not depend on the number of samples. It's constant. It only depends on the hypothesis class and it depends on the ground truth, f of x, what it is. Now what about the variance? Will it increase with n? Will it decrease with n? Will it become, it of course depends on d. What's the general idea? As you have more and more training points, do you expect the fluctuations to be higher or to be lower? You expect it to be lower, so the variance will decrease typically with n. Right? So your variance would be a function that decreases with n, and so if you sketch E out, which is the average bias plus the average variance, E out might look like this. So this at any point is the variance. So the variance is going to decrease. So if you were to just sketch the variance on its own, it will be decreasing and eventually go to 0 if you have enough points, right? Assuming it's a rich enough set, so the points are IID and so on. And so when you compute E out, which is the bias plus variance, it will be a function that looks like this. Now, if you have a simple hypothesis, the variance will be small, right? So E out will quickly converge to the bias. You cannot decrease beyond the bias because E out is the bias plus variance. If you have a complex hypothesis, you will converge to the bias eventually, but you will need a lot more points. So initially your variance will be much higher. So what will happen is, if you have this complex case, maybe your E out looks like this. It's very large, it starts at very large values because you haven't converged here. And eventually, if you have enough number of samples, you will get to this point. So for any n, the variance in the complex hypothesis class will be much higher than for the simple hypothesis class. But eventually, if you had a lot of samples, then the complex hypothesis class will win because now the variance can be made as small as you like. Its bias was small to begin with, so you will converge to a smaller out of sample error. Yeah?
Sorry, when you write the variance equation there, isn't that the square of GD minus GR?
Oh, that's my mistake. Thanks. And those are all bars. So the summary is that if you have a simple model, versus complex model. Look at the bias. The bias for a simple model will be high, right? For a complex model, the bias is going to be low. If you look at the variance, for a simple model, the variance is going to be low. And for a complex model, the variance is actually going to be high. And the final error, after you have enough number of samples and things have converged, for a simple model will continue to be high because you can never go below the bias function. For a complex model, the final error will be low, but you will need a lot of data points, which is what you see in this figure here. So this completes our discussion of bias variance trade-off. This is also in chapter 2 of the text. You will do quite a few examples next week in the tutorials, so you can really familiarize yourself with all the definitions. I know it's a lot of things, but once you do a few examples, everyone will be comfortable with it. We'll move on now. Unless there are any questions, we'll move on to next topic, which is chapter 4 of the text. Any questions? Final questions?
Yeah, what do you mean by trade-off?
It's because typically it's this thing, right? Like if you have a simple model, the bias is high, whereas for a complex model, the bias is low, and the variance is opposite.
So because just like for a particular mode of the bias is a constant, right?
For a particular hypothesis class, the bias is a constant. But you want to decide whether I should choose, say, first order polynomial, like linear models or quadratic models or polynomial models. Each one of them will have a bias and a variance. The bias will start decreasing as you make the model more complex. The variance will start increasing. And you want to minimize the sum of the two. So the right model will be one for which the bias plus variance is smallest.
Again, why variance will be decreasing?
Because you have more sample points, you have more data points, so the fluctuations will be small, right? Imagine you have a second order polynomial for as your hypothesis class, you have 10 points versus 100 points versus 1000 points. Then the fluctuations of a given sample with respect to the mean will be much higher if you have 10 points, say. But it will be much lower if you had 10,000 points. Right? So imagine, or if you just go to this example, let me just come here. Imagine you had this thing, right? And I am going to give you 2 points now, and I'm using a linear model. If my 2 points are like this, let's say the 2 points are like this. This is U1, U2, V1, V2. And I use a linear model, right? My output will be the best fit, the best line that goes through the 2 points. So it might look like this. It can have very large variance. But imagine I had 10 points. So I had like this, but I had 10 points, maybe, or some number of points. So now I have all these data points. And now I'm going to fit a line that is going to be consistent with all these points. It won't have zero training error, but it will be much more stable. So this one will have a much higher, this first case when n is 2, you will have a much higher variance than when n is 6 or something. That's the intuition. Because you have more data points, the output will be stable. Any other questions? They're all great questions. You should get the intuition. Okay, so now we move on to chapter 4 of the text, which is validation. So we move on to another topic where we are still interested in the same question. What model to select? Should we select, given a training set, should we select a simple model or should we select a more complex model that gives the best test error, minimizes the test error? In chapter 2, we took a theoretical approach. For classification, we used bounds using the VC dimension and Hofding's inequality. And so we had a bound on E out given E in terms of the VC dimension. And then for the regression problems with squared error, we had the bias variance trade-off. So these are theoretical ways of understanding what is the right model to select. Validation, which you have already done in assignments, is a more empirical way and a more direct way. So I'm getting an output from my training set and I want to estimate what the test error is, right? So this is another way of giving an estimate of the test error. So what we will do in this chapter is provide a more rigorous treatment of validation. Instead of it just being a completely empirical estimate, we'll provide some theoretical guarantees on validation error and study it in a bit more rigorous fashion. So again, our goal is to find a relation between the training error En of g, which is 1 over n, summation of n going from 1 to n, E of g of xn and yn, and the test error. So E is the loss function. It could be the squared error, it could be the classification error, and so on. And the test error E out of g, which is E of g of x and y, and you take the expectation with respect to our data vector x. So we want to relate the two quantities, the training error and the test error, right? But instead of using the theoretical bounds, we will use validation sets. So the idea in the validation set is basically what you have been doing in the assignments. If you have n samples, you don't use all of them for training. You split the input data set into two parts. Some of them are used for training and the others are not used for training. They are used to provide an estimate of the test error. This is the validation set. So the idea is that if you have our training set D with n samples, you split it into two parts. You split it into training set, which will consist of n minus k samples, and you split into validation set, which will consist of k samples. You only use this part for training. So you do not use all of your data for training. And you get an output candidate model. When you use that model, evaluate the performance on the validation set, and the error you get is an estimate for your test error. So let me do that here. So instead of using the entire data, if you take D and pass it through the learning algorithm, your output will be G. This will be your output. But if you have this, you cannot easily estimate the test error. So we will not do this for now. Instead of this, we'll take a smaller set. The training set, will pass it through the learning algorithm, and we'll get an estimate G minus. So G minus will not equal G in general because you have fewer points. Here we had n data points. Here we have n minus k data points. We have thrown away k points, put them in the validation set. So the output will not be the same as G. There is a discrepancy, and so I'm writing G minus as my output here. This is not G bar, but that we defined before. Don't confuse this with G bar, right? G minus is just the output with a subset of data points. Now what we do is we compute eval of G, the validation error associated with G minus, which is 1 over K summation over all data points in dval of E of G minus of Xn and Yn. So we take the error, we compute the error on the validation set. So we take all data points in dval, the K points, average it with K, which is the size of the validation set, and compute the loss on each of the points in the validation set. Now the validation set was never used for training, so it's a clean set. There's not going to be any bias in how you in this error. And the question is, how well does eval of G minus approximate E out of G minus? So any ideas? Can anyone give any guarantees on how the relation between eval and E out? Are they exactly the same? Will eval of G minus be exactly equal to E out of G minus? Yes, no, why not? If no, yeah?
The validation set might have like a different, like the testing set will be a different data set, right? Compared to the validation set.
So imagine all the data points are generated IID from the same distribution PX. That is our working assumption. Like in chapter 2, we said that all the data points, D consists of n points, x1, x2 up to xn. All of them are sampled IID from the same distribution Px. So in a sense, and when we do the test, we are generating a random data point from the same distribution and then taking the expectation. So it's not like the distributions are different. Okay, so what I'm saying is, D consists of n points. And they are all generated IID from the distribution Px, and Yi is f of xi, where f is the unknown function. So it's a fair game. Like we are not going to change the distribution for validation, and so it's a different data set, but coming from the same distribution. Okay. So the question is, now what I'm doing is I'm going to use the first n minus k points, say, put them in the training set, and obtain the output G minus. The remaining k points I'm going to use for validation. So I'm going to average the loss over this remaining k points, which were never used in training. And now I'm going to try to estimate the test error, right? Which we defined on the previous slide. This is E out. So this is the expected value over X of E of G minus of X and Y. We want to approximate this using eval of G minus. So the question is, are they going to be exact? Is eval exactly equal to this? Is it approximately equal to this? And if so, where is the approximation? If k equals infinity, so I think the point made before and now is that k is finite. So eval is changing. It's a random quantity. Eval is not a deterministic quantity because you're taking average over dval, right? And dval is also drawn from this distribution. So if you fix G minus, E out is fixed. It's a deterministic quantity. But eval of G minus is still random because you're averaging over a random set of points. So k might be like 5, right? Then you're averaging over 5 random points. Whereas E out is a deterministic quantity once G minus is fixed. And so what was said is if k is infinite, then the two will be the same. This is true. So eval of G minus will converge to E out of G minus as k goes to infinity. So we'll write a more precise relation between the two. But But any questions before that about the notation, the setup? What if I take the expected value? See, we said eval of G minus is random, right? Because dval is random. What if I take the expected value over dval of eval of G minus? There's a lot here. So if I take this quantity and I take the expected value with respect to dval, any idea what that will be? So what I'm doing here is for a given dval, I'm taking the average over those points, over those k points. Now but those k points are themselves random, right? They are random because we are sampling them IIDPX. What if I take the expectation with respect to dval? Any idea what that quantity will be? Is that random or is it deterministic? We'll assume G minus is fixed. It's coming out after training. For this G minus, depending on my choice of dval, I will get some quantity here, depending on which data points I have. Now I'm taking the expectation with respect to this set dval. So will that quantity be random or will it be fixed? It's going to be fixed because now I'm averaging out the effects of dval. Any idea what that quantity will be? It will actually be this quantity, E out of G minus. Right? Because as k goes to infinity, we said that this quantity will converge to E out of G minus. And so taking the expectation is like taking infinite number of points and averaging it out. So let me write that. So properties. The first one is that if you take eval of G minus, this is a random quantity. So let me first write is random because dval is random, right? The data set that you generate. So let's just for notation say that dval is x1, the first k points in our training. We split it so that the first k points are in dval, the remaining points are in the dtrain. So this is random. Now, if I take the expected value of eval of G minus and take the expectation with respect to dval, this is in fact going to equal E out of G minus. This will be the test error. This is known as the unbiased estimate. So for any k, your eval is going to be a random quantity because these points are random, right? And so your estimate is a random value, which is what you have. But what we are saying is that in expectation, this estimate will equal the test error. Or in other words, if you take infinite number of points and evaluate eval, it will equal the test error. So it's an unbiased estimator. In the limit of large number of points, there is no difference between eval and E out. The other property is the following. With probability greater than 1 minus delta, so with high probability, it turns out that E out of G minus will be less than eval of G minus plus this quantity 1 by 2k log 2 by delta. This is also true. So now eval is a random quantity. For each k it's a random number, right? But what we know is that it is not too far. It's going to concentrate around the test error. In the sense that if for any eval that you get with very high probability, it is going to be, the test error is going to be eval plus a quantity that decreases as 1 over root k. It's 1 over square root of 1 over 2k log 2 over delta. You can show this. Can anyone see why this would be true based on what we have studied so far? Like where would a relationship like this come from? So remember, eval was defined here. It's the average over the k samples, right? E out is the expected value. Eval converges to E out as k becomes large. So, or even here, the expected value of eval is E out. So why would this be true? Anything? Does this ring any bell? So recall eval is 1 over k times summation. Since we are defining dval to be the first k points, it's the k equals 1 to capital K E of G minus of xk and yk. This is what eval is. And E out, this quantity, is the expected value by definition of x of G minus of x and y. This is the test error, right? So you get, so here you are getting k independent points, x1, y1, x2, y2, and you're evaluating G minus on these k points. So you're computing the loss function on those k points and taking the average. E out is basically saying that you take a random point x from the same distribution, compute the loss, and then take the expectation. And what we are claiming is that the gap between eval and E out is upper bounded by this particular penalty term. So why would it be that this relation holds true? Is this similar to something we have seen before? Yeah?
Because it's a subset of your training data, so the same upper bound holds that it did for E and
Yeah, so right now, we had n points, right? We used n minus k for training. So G minus was trained on n minus k points. So imagine we had 1,000 points. And we used the first 100 in the validation set. K was 100. And we used the remaining 900 for training, right? So the first 100 are just kept aside. They're kept in a log. The remaining 900 points were used to generate G minus. Now once I generated, so imagine I was training a linear classifier. So I used SGD. So I trained this classifier on this 900 points and I found my best hypothesis, the best line. That is G minus, right? Once I have this hypothesis, so we'll prove two first. So G minus is selected through detrain, right? So we take this subset, we pass it through the learning algorithm, and we get G minus. This does not depend on dval. So as far as d-val is concerned, G minus is some fixed hypothesis selected before looking at d-val. Okay? And so we go back to the easiest case we had in chapter 2 where we had a fixed hypothesis. D-val was our, like eval is like our training error, E-out is like the test error, and we want to compute the difference between the two. It was like the case where we had a jar with red and green balls. We were taking out the balls and estimating the fraction based on the observation. It's that example, right? Before the union bound was applied and so on. So then probability E out of G minus minus eval of G minus greater than epsilon is less than 2e to the minus 2k epsilon square. Here instead of n you have k, the size of the set is k. You're computing your quote unquote training error on k points instead of n points as we had there. It's exactly the same setup. And then from this we get the second bound. Okay, is this clear? So I had promised that we will have applications of the simple bounds. This is that application. Now the proof of one is just technical. It's not really, it's basically we'll do the proof of one for completeness. I think you all have the intuition. What we want to show is that the expected value over d-val of eval of G minus is E out of G minus, right? So the expected value over d-val is the expected value over the data points. So expected value of x over x1 to xk of eval, which is 1 over k summation of k going from 1 to k, E of G minus of xk and yk. Okay, this is the definition. So now we can do a term by term expectation. We're doing one term at a time. So this quantity only depends on xk and yk, right? One variable. Here we are taking the expectation with respect to x1, x2 up to xk. But the only variable that matters is x little k. So if we take k equals 1 here, then you have E of G minus of x1 and y1. So when you take the expectation, the only quantity that matters is that particular random variable. Okay? You just marginalize out over the rest, they are not relevant. Now, any idea what this quantity is? Expected value of E of G minus of xk and yk with respect to xk. It is E out, right? Again, that's a definition. Because G minus is selected from the training set, it's independent of all the data points in the validation set. This is like you get a random xk, you compute the loss of that point, you take the expectation with respect to xk. This is precisely the definition of E out of G minus. So all of this is basically each term is E out of G minus. So this reduces to E out of G minus. This was the first one, the first property. We had two properties. One was the expected value of this quantity is E out of G minus, which we intuitively agreed. This is a proof of it, fairly straightforward. The other one is a high probability bound. That it's not just that in expectation they are the same. The variance, like we also have a high probability bound, uh, like this one. So with high probability, eval and E out will be close. The gap is at most 1 over root of 2k. And you can do other things as well. So eval is random, but if you look at the variance, then the variance of this quantity decreases as 1 over k. You can also show that if you add more and more points in the validation set, the fluctuation around the mean, so the fluctuation of eval around the test error will become smaller and smaller. We won't prove this because the proof is very similar, and the point is that the variance will decrease with k, the size of the validation set, as 1 over k, and so on. So the bigger the validation set, the better your estimate is. All these results say that if you have a big enough validation set, then your validation error will be a very good estimate of your test error. The question is, why will you not want to have a very big validation set? What stops you from having like all points in the validation set? Yeah? Yeah, you'll have a very small training set. So G minus is not going to be a good model to begin with. It will give you a very high error to begin for your test error, which is not what you want. So imagine that you have a medical application where you have 100 patients. Collecting data for each patient is very expensive. It might take hours of like a medical scan, many things. It might be expensive. You don't even want to throw away 1 point. You want to use all 100 points for training, right? Because collecting data can be very expensive. So even like throwing away a fraction of it may not be desirable. So what you really want, ideally, what you want is the following. You can only compute eval of G minus. You want eval of G minus to be close to E out of G minus. But ultimately, you are going to use the entire data set for training. And your output will not be G minus, your output will be G, right? Like the one that is trained on the entire data set. So you want E out of G minus to be close to E out of G. So you want two approximations to hold at the same time. Eval should be close to E out, and this requires K is large, so that this is a good approximation. But you also want E out to be of G minus to be close to E out of G, the one you get by training the entire data without splitting. This requires N minus K is large, or K is small. If N minus K is large, then G minus and G will be close to one another, because you have essentially used all the data for training. And so there is a tension between the two. This part requires K to be large, this part requires K to be small. And a typical rule of thumb, which is often used, is to take K to be N over 5. So you use 20% for validation. It's not always the case, but it's a good rule of thumb to have, 80% for training. This is a reasonable practical choice people make. Sometimes people do 1/3 and 2/3. There are other ways, but depending on the application, but this is a reasonable starting point. Anyone know in assignment 3, what's the validation size? 1/3, 2/3, I think that's right. Okay, so the next topic is to build up. So far we have used validation set for only one purpose, which is to estimate the test error. Now see how to build upon this. The next thing to study is model selection. In model selection, the idea is basically that you are given a training set and you want to decide what is the right model. Should you use a linear model, second order model, 10th order model, a neural network, and so on. What is the right model, machine learning model to use for this data set? So we are given a training set D, or given a data set. Let's not call it training set because we are using a different term for training now, with n points or n samples. And consider candidate hypothesis class H1, H2 up to Hn. And the question is, which of these hypothesis class is the right one for this data? So H1 could be linear models, H2 could be second order models, H3 could be third order models, some of them could be neural networks, and so on. Right? Well, some of them could be one layer neural network with 50 hidden units. Others could be like, deeper neural networks, and so on. So which select the best hypothesis class? This is the problem in model selection. So there is a natural extension of what we just discussed. I'll move on to the next slide. Everyone is done. So the idea is we take D and we split it up again into D train, which is n minus k points, and D val, which is k points. Okay. Then what we do is we have M hypothesis, H1, H2, H3 up to Hm. We take the training set and we train each of the hypothesis class on the training set. So we take D train, we train it on hypothesis H1, we train it on hypothesis H2. So when we train it on H1, if H1 is the set of linear classifiers, we'll get the best output, the best linear model. We'll call it G1 with a minus because we're training it on a subset of points. This will be called G2 minus, G3 minus, up to Gm minus. So these are the best hypotheses in each of these classes. So you may run maybe stochastic gradient descent, minimize the training error, you may add some regularization if you like, doesn't matter. For each model, will produce the best candidate. So the best linear classifier, the second order classifier, and so on. What you get from that class. Okay. So then what you do is you take dval and you apply it on each of these candidates. So now you get eval of G1 minus, eval of G2 minus, Okay, you can compute the validation error for each one. Now, question: if you make the hypothesis class more and more complex, if you go from a simple model to a complex model, what would happen to the training error? What would be the training? How would the training errors behave? It will keep decreasing, right? The linear model will have the smallest error. The second order model will have the largest error. The second order model will have a smaller error. The third order model will have a smaller error, and so on. So if you just looked at the training error, then you will naturally look at the most complex hypothesis and select that one. But will the validation error also decrease? In general, it will not, right? Because maybe you are overfitting for most complex models and you would rather prefer something in between. So you may want to maybe select one of those models where the training error is not that small, but the validation error is actually the smallest. The validation error will be our approximation to the test error. And so we will select a hypothesis for which we will have the smallest validation error. That will give us our choice of the model. Okay. Now, once you have this hypothesis, so M star is the selected hypothesis. Now, once you have selected our hypothesis, you go back and train it on the entire set D. You should never leave points out. And then you get G, which is the output hypothesis, which is going to be an element in HM star. Okay? So the idea is that you do this splitting and so on just for the sake of selecting the right hypothesis class. Here you want to make a decision of whether you want to select a linear model, a second order model, neural network, and so on. Once you have selected the hypothesis class and you have to output the actual model, you should never throw away any data points. You should use all the endpoints. If you had 1,000 data points, use all 1,000, don't split anymore. And use those 1,000 points to train the best hypothesis class and get an output G. Now G will not necessarily be any of these. If you were to just use D train here and train it, you will get GM star minus, right? But that is not the best choice. You should not live with less amount of data for training because every point can be potentially very important. So the final output will always be G. So we'll call it G sub M star because it's from the hypothesis class M star. And this will be our final output. Is this clear? So basically in the first step, what we do is we split our data into the training and the validation. Then we take our training of n minus, so k is typically n over 5, again as always. Then we will take the training set, we'll train each hypothesis class to get the best hypothesis in that particular set. So G1 minus, G2 minus, and so on. So then we compute the validation error for each of them. We select the hypothesis set for which the validation error is the smallest. Once we have selected that set, we perform the training on the entire data set D, not on the subset. And this is how we get the output. What we want to do is we want to get an estimate for ideally we want to get an estimate for our test error. We want to compute this quantity. Okay. Now what have we computed? For what we have computed is that for m equals 1, 2 up to m, we have computed eval of gm minus. This we could compute. For each hypothesis, we trained it on dtrain and then computed eval, the validation error. Now, naturally, what we want is that eval of gm minus should be close to E out of gm minus, or E out, the test error at gm, and that should be close, or at least for m star, the one that we do compute, it should be close to E out of gm star. This is the approximation we want to have. For the m star that we select, we want to have this property. And the question is under what conditions this holds. So let's not worry about the second approximation for now. We'll assume that n minus k is large enough so that that holds. We'll only focus on the first approximation. So we will try to focus on this approximation. Under what conditions is eval of gm star minus the same as E out of gm star? So what we have computed is, for each, we have computed this quantity. Eval of gm minus is 1 over k summation of k going from 1 to k, E of gm minus of xk and yk. So this was computed in our validation, computing the validation error. Then we selected m star to be argmin of eval of gm minus over m in the set 1, 2 up to m. Right? So I have two questions here. One is that, is it true that for each m equals 1, 2 up to m, eval of gm minus, when we take the expectation, is E out of gm minus? And the second is this true when I replace m with m star? So this the question. So now eval of gm minus is a random quantity, as we discussed before, because dval is random. These data points are random. So if I take the expectation with respect to dval, is it true that it will equal E out, the test error for gm minus? And secondly, if I replace m with m star, the best hypothesis selected, is it true that this will equal this quantity? Any ideas? So what I'm doing is I have the training set, dtrain, of n minus k points. I'm using them to compute g1 minus, g2 minus up to gm minus, right? Now I'm going to compute the validation error for each of them separately using the dval. So I'm going to use this to compute the validation error for each of the gms. And the question is, will that in expectation equal E out? Will this converge to E out if k goes to infinity? That's the first question. And the second question is, if I select m star based on this, is it true that this relation holds for m equals m star? Yeah?
I want to guess that the first one is true, but the second one is false because m
star is chosen based on the validation set?
That is exactly right. So M star is selected adaptively after looking at the validation set. So GM star is not a fixed hypothesis anymore. It is selected after you look at this candidate hypothesis G1, G2 up to GM and select the one that performs best on the validation set. It's no longer a fixed hypothesis, right? So for this relation, it will be true because of the property we discussed before. The GM minus was a fixed hypothesis as far as the validation set is concerned. It was selected only from the training points. So we use dtrain to select this. So from the point of view of dval, G1 minus was some fixed hypothesis selected without looking at dval. And we're computing eval of G1 minus. So surely this was a very good approximation to E out, right? Because eval of G1 minus then is the empirical estimate of E out. And so the result we discussed before applies to eval of G1 minus. Similarly, G2 minus was some fixed hypothesis. So the result we discussed before applies. So for all of them, this relation holds. The expected value of dval of eval of Gm minus will be E out of Gm minus. Because these are like fixed hypotheses, we are doing an empirical estimate of the loss function, and that will converge to the expectation. So that works. The problem with M star is, although M star is 1 out of 1, 2 up to M, it is selected adaptively. So you have M star, this M star is a function. This depends on dval. It's no longer a fixed hypothesis. M star is selected by looking at eval and then picking one that minimizes the validation error. So the choice, sometimes M star might be 1, sometimes M star might be 2, depending on what the validation error is. So M star is changing. It's an adaptive selection now with respect to dval. So this relation will no longer hold. So it's not true. So if I were to write this in other words, what we know is that for each M, fixed M, we'll have that E out of Gm minus will be less than eval of Gm minus plus 1 by 2k log 2 by delta. This was the second property. High probability bound holds because Gm minus is a fixed hypothesis as far as the validation set is concerned. But it is not true that E out of Gm star minus is less than eval of Gm star minus plus 1 by 2k log 2 by delta. This is not true. Okay. Although M star is only one out of these M values, and for each of them this holds. So this happens with probability greater than 1 minus delta. For each fixed M, this will hold. For M equals 1, this will hold. For M equals 2, this will hold, and so on. And M star is 1 out of these M values. It is either 1, 2 up to M. But because M star itself is random, it turns out that this event is not going to be true. Because now you have randomness that comes from M star as well, which is in play. And so it's actually going to affect us negatively, and it's not true that this event holds with probability 1 minus delta. This does not work. Once you make M star a random quantity dependent on dval. For each fixed M, it will hold. It's a subtle but important point. So then, if you understand this, if there are no questions, how will you fix this? How will you get a bound on E out of Gm star minus that holds with probability 1 minus delta? This is too optimistic a penalty term. So how can you fix this penalty term so that this bound will hold with probability greater than 1 minus delta? First, are there any questions why this does not hold and this holds, even though M star is 1 out of those M events? That is clear. You should be able to answer the second question.
You have a test set that's outside of the bounding.
No, we want to give theoretical. We are not going to change the setup. We'll use the same setup. We just want a suitable penalty term here. So it is true that if we use another set, so if we did 80, 10, 10, right? It is true that if we did that, and then what we would do is we would compute not on this, not on the validation set, we will compute it on a completely fresh sample. Then the bound will hold. So that was the point made, that is accepted, that can be done. But we don't want to, again, keep dividing because then we will have very few data points in each set. There are other issues. We just want to fix this bound where we are evaluating eval on the same set on which M star was selected. So we are not changing things there. So this is how M star was selected. I had it on the previous page. So M star was selected using this rule. So it is dependent on dval, but via this particular selection rule. You compute eval for the first candidate, for the second candidate, for the third candidate, and pick the winner, the one that has smallest eval, right? That's how the dependence happens. And you use that, yeah?
The problem still holds for the second worst.
So this holds for every m.
Yeah.
Does not hold. So for G1 it will hold, for G2 it holds, and so on. So, but the point is that even though M star, so let's say M is 2, right? You either have G1 or G2. This bound will hold for G1, this will hold for G2. But if you were to select M star to be the hypothesis for which eval is smaller, if eval of G1 is less than eval of G2, select M star to be 1. Otherwise, select it to be 2. Then this bound will not hold for that M star. Because M star is now random, depends on your data set. And so suddenly, all of a sudden, this bound is no longer true. Because it's not a fixed hypothesis.
Just
Sum up all M. I don't quite understand what, how, where. Here in this expression, so you're saying just sum up on both sides. But it's not like you're computing the average of this, right? This is going to be, this can be much larger than the average because the average is still for a fixed hypothesis. This is now going to be adaptive. It's actually dependent on the data set.
Do we use union bound?
Okay, we are getting there. Sure. How would we use what union bound?
So it will be either one of them. So we use the same analogy which we did.
That's right. What happens now is that Gm star belongs to the set G, which is G1 minus, G2 minus, up to Gm minus. Okay? Gm star is an element in this set. It's either G1, G2, G3 up to Gm. Now, each of them were fixed hypotheses selected before looking at the data. Each of them were, because they were selected using D-train. So as far as dval is concerned, these are all fixed hypotheses before observing dval. Now this output is selected after observing dval. And we looked at this case. This is the case when your hypothesis set is finite. It has m elements and you're allowed to select one adaptively after observing your training set. We looked at this case. This was the second case and we used union bound for this, right? So what we said is that in this case, we can apply Hofding but with the union bound. And that's exactly what we'll do here. So all these cases that we dismiss, saying, well, in machine learning, well, if even for a linear model, you have infinitely many hypotheses, all of that is true, but even the finite cases are all useful when we study this validation problem. So can anyone remember what the bound will be? How do I bound probability E out of G minus minus E val of G minus? What will be the bound here? Well, it's not quite Hofding, it's not quite this. I have to fix it by putting an M there. That comes from the union bound. Okay. So what we get is E out of GM star minus is less than E val of GM star minus plus a constant that will decrease as log M by K. So instead of just 1 over K, we have log of M over K, where M is the number of different hypothesis classes that we had. So if we tried linear model, second order model, neural networks, each one contributes to one term in M. So it's a number of distinct hypothesis class. The key point here is that this bound, the penalty term, this penalty term is not dependent on the VC dimension. So you could have very deep networks, very big networks with very large VC dimension. But your penalty will still be not dependent on the VC dimension. It just depends on the number of hypothesis classes you have that you use to validate against and then pick the best one. So you may have a convolutional network with 1,000 layers, a deep neural network which is very wide. So they all have very large VC dimensions, right? But if you are only using these two classes and you're training over them and picking one, then your penalty term will still be very small. It will just be log of 2 by K. So you get a big gain here by this approach compared to like just fully training on and using all the data for training. So any people still writing this? Anyone still writing? Please. So what we are doing here is, let me just write one thing. So we have M hypothesis classes. H1, H2, up to HM. We do not know which is the right one for our data set. So we want to pick an output hypothesis that belongs to the union of H1, H2 up to HM. Our output is somewhere in one of these classes, right? So what we are producing is an element which is in H1, union H2, union H3, and so on. So our output G belongs to H star, which will be H1, union H2, up to HM. That's where the output will lie. It will lie somewhere in this set. So imagine that we just used H star, we directly trained on this and produced an output. Instead of doing this two-step approach, imagine, so consider G hat to be argmin of E in of H, where H belongs to H star, which is H1 union H2 up to HM. So we just exhaustively find the hypothesis that gives the smallest training error in this union. Okay? Instead of doing the two-step approach where we use validation set for model selection, select the model and then do training on it, let's say that we just did like a search over all possible hypotheses and in this set and picked one that minimizes the training error on the entire data set D. So no splitting and model selection. Can anyone give me a relation between E out of G hat and E in of G hat? How will that depend? So H1 could be linear models, H2 could be second order models, there could be some neural networks here, and we look at all possible candidates and pick one with the smallest training error. So first, which candidate, which model is likely to be selected? Linear, second order, neural networks, which one will be selecting? The most complex one, right? So ideally a neural network. Now can we give a relationship between the output test error for this and the training error here? How do we relate the two? What will be using? So it will be, we want to say that the test error is less than this plus some penalty term. So any idea what the penalty term will be? Or what will it depend on? Did this before, perhaps last week. Depends on the VC dimension. dVC of H star log n by n. It will scale in this fashion, right? That's how you get generalization bounds. This is purely a problem where you have some hypothesis class, you're choosing a hypothesis from this class that happens to minimize the training error. Then what we know is that the test error and the training error are related via the VC dimension. It's square root of the VC dimension times log n by n. Now, the VC dimension for this hypothesis class can be very big. If you're using complex models like neural network, this term can be huge. So this can be dVC of H star can be very large in practice, right? So that's why this will be, in general, your E out will end up being very large here because the penalty term can be huge. If you're using complex models, then this penalty term can be extremely large, even if E in is small, which it will because you're doing an exhaustive search over all models. The second term is going to be overwhelmingly large. So you're really going to be overfitting here. The other bound we had for model selection, we had that E out is less than E val plus a term which is much smaller. The penalty term here does not depend on the VC dimension. It's just square root of log m, where m is the number of classes you have divided by k, the size of the validation set. So here you do have n, which is going to help you somewhat. There you have k in the denominator. But typically k, if we select it to be n over 5, then this term is still going to be much larger than what you get here. If k is n over 5, you still get n here and like 5 log n. So this is always much more preferred than an approach that does not use validation for model selection and just tries to find one with the smallest training error. So this is not recommended. People see the difference? Contrast of two approaches. Is it clear what we are doing here? Here we are not doing the two steps. It's not like we are selecting a model that has a small validation error and then training on that set, right? Here we are taking all possible hypotheses that we are allowed to have. Linear models, neural networks, convolutional neural networks, finding the one that fits best on our training set. This is going to be usually giving a lot of overfitting. And the way we see that is that even though the training error is small, the test error will be bounded by the training error plus a penalty term. The penalty term will depend on the VC dimension of the entire set we are going to select, which is the union of all the hypotheses, H1, H2 up to HM. And so that will have a huge VC dimension because we have a very complex space to search over. And so this term is going to be very large. So to show this, we'll finish with the following diagram. So imagine that we are plotting the error as a function of the size of the validation set. K, right? Now let's say we first try to plot E out of G hat. We plot this quantity where we do not use the validation set. Can anyone guess how it will look like, what the shape will be on this plot? Yeah? It will be a constant line because it does not depend on validation. It will be some large value because it's generally very bad. You're overfitting, right? So E out of G hat will look like this. Now let's try to compute. E out of G minus M star. We argued that it is less than eval of G M star minus plus a term that decreases as log M by K. So now let's call this term 1 and let's call this term 2. Let's look at the case when K is small and K is large. When K is small, which of these two terms will be smaller? The first term or the second term? Or let's look at them one at a time. When K is small, will eval be generally smaller or larger? Any guesses? Let's take a vote. How many think it's small? That's the right answer because when K is small, N minus K is large. So you're training the hypothesis on a rich enough set. So you will have a good output. So GM minus, this outputs will be good. And so eval is basically obtained by training over a rich hypothesis set. So T1 is small. What about T2? Well, it decreases as 1 over root K. So T2 is large. So initially, you might be, let's say, somewhere here. Now, as you increase K, let's look at the other extreme. If K is large, what happens to T1? Will it be large or will it be small? You make K to be very big. Okay, this will be large because now you have a very small set, so you have very noisy training. So T1 is large and T2 is small. T2 is small because this is going to be small, so you have a good approximation between the validation and the output. So the way the shape for this function will look like is it will look like this. This will be E out of G M star minus, right? So what is happening here is initially, because this part is small, your validation error is going to be a very noisy estimate of the test error because you're not averaging over enough samples. As you increase K, the estimate for G minus is not going to change much because you still have a big training set. So this won't change much, but you will get an improvement here. So the validation error will decrease. You will get to a sweet spot of the optimal validation set where these terms will balance each other out. After that, what happens is you will start decreasing the size of training set. So you'll start decreasing, like your estimates for the output models will start becoming more and more noisy because you don't have much training set. But then this term is going to be too good, but that's an overkill because your models are not being trained well to begin with. And that's why it will start shooting up. So this again shows that selecting the right value of k is important. And typically, again, k equals n over 5 gives you a good choice in terms of what strikes the good balance. So I'll stop here because it's 8:50 and we didn't take the second break. Next lecture, we'll start with something called cross-validation. And cross-validation, in a sense, is getting best of both worlds. You can keep the size of the training set large, you can keep this quantity small, and surprisingly, you can still keep this quantity small. So it's a very popular technique, and it's good to understand it. So we'll start it next lecture.